Hello there, good evening. So, I've promised that I will make a video regarding this topic, electromagnetism, chapter 3, KSSM physics, form 5, right? So, the previous chapter is regarding electromagnetism, and we are going to dive through several fundamental or actually childhood questions in this topic. And yeah, let's start with what is actually electromagnetism by definition, because it's quite interesting. Previously we have learned electricity, and now we are going to learn electromagnetism. If you realize that electromagnetism is the combination of two words actually. First one is electro, or we can simply say it's regarding electricity, previous chapter, chapter 2, and magnetism. So it's all about electric and magnet, right? But if you see the magnet, how is it related to electricity, right? So that's why we are going to learn together how they relate, right? And yeah, we just add electricity with magnetism. That's where the topic comes from. You can think like that. And yeah, let's give few example of magnets. So maybe you have familiar with this U-shaped magnet, okay, which is a permanent magnet. You can see the red part is actually the north pole, and also the blue one is the south pole, right? And maybe you can say the circular magnet, bar magnet, and also even compass is a magnet, right? Magnetic needle. Okay, so as we know that compass, it shows directions, but how is it possible? How can the compass shows directions, right? I mean, how's the mechanism works? And that's why we are going to answer several questions in this topic. But before that, do you know what is the strongest magnet pupil ever invented? So maybe you have heard about this neodymium magnet. So you can search on the internet. So you will realize that this magnet is perhaps the most strongest one. Okay, and it can be dangerous if you have the big one, because the magnetic force is very massive, and when you have two magnets attracting together, so they can crush, okay, even your hand if you put between the two magnets while they are attracting. And yeah, it can even cause injury, so be careful when playing with this magnet. And the second question is, do you know what is the largest magnet in the world? Yeah, I mean the largest one in the world. So our world itself is the largest magnet, believe it or not, right? The earth itself is the largest magnet. But how is it possible, right? How can the earth become the magnet? And what is the tiniest magnet in the universe? So perhaps you ever discovered it during your chemistry class. Is it electron? So electron is the tiniest magnet, and in fact electron is the cause of the magnetism of the magnet. So it's the cause, and the effect is the magnetic properties of the material or object. But in this chapter, the subtopic is supposed to be the current carrying wire, mostly about that. But we are going to answer how to create a magnet. So how does a magnet becomes a magnet, right? So that's perhaps the childhood questions, most of us. And the second one is, what is electromagnet? So this is appear in your syllabus, electromagnetism, about electromagnet. So how it turns, let's say, steel or iron into magnet. So it's kind of counterintuitive when we watch like science TV program. So have you ever wondered that why I mean, when you let's say when you connect this, let's say, steel nail to the, let's say, the battery source, and then you just coil around the wire, and you realize that this nail steel can behave like a magnet. How and why, right? And some more questions. One more question is, why some objects can behave magnetically but some don't, right? So it's like intriguing when we think about why plastic, or why even the glass, cannot attract, let's say, iron or steel, right? So it's very interesting to find out. Okay, maybe this is the most I think the most nauseous thing that I have done during my childhood is, yeah, let's say I have a magnet in my hand. You know, the magnet toy, when you can find it in the sundry shop. And then when you put the magnet close by the, let's say, television or electronics, so you can see this kind of like patterns, or like a rainbow colors and patterns you can see. And you might think, when you learn physics, electricity, you can kind of like relate with this pattern, electric field, right? When you learn electricity, you have positive and negative, let's say, charges, and then when you just put them nearby, okay, so you can realize that there is a imaginary lines we call a field, electric field, and you can see this kind of imaginary pattern um, trace on this, let's say, TV screen, right? So it's similar. So have you ever found that? I mean, have you ever been curious about that? Why is it similar? Because of the electromagnetism properties, because they are related, right? And this pattern you see is actually magnetic field, right? And we will discover more in the next subtopic perhaps. And this is earth magnetic field, right? So magnetic field and electric field somewhat similar, but the source is quite different, because in electric field you have two charges, but for magnetic field you have two poles, north and south, right? And of course the field line, imaginary field line, sourcing from the north to the south, right? And this is electrons, so of course you know electrons is the tiniest magnet. That's why magnet can becomes magnet due to electron behavior. So because of this electron moves, then we have electricity. So that's we have learned in the previous. So current occurs, or current exists due to the motion, or I could say due to the electron moving inside the circuit, right? Creating current, because current is actually the rate of change of the charge, okay, dq over dt. So pole of the magnet, in the previous chapter we have learned that this, okay, when we have parallel flat charge, positive and negative, so you can see that at the middle between them, so we have a flat, what we call the electric field, but at the bottom and the top of it, we can see that the field line slightly curved. Why? We have answered this in the previous class, because of the because at the top and the bottom of this plate, so we have the change of the field. So the field line is not constant here, so we have the gradient of field at the bottom and top, so that's why it's slightly curved. And yeah, what is pole of magnet, by the way? So it's a region, it's a part or place in which the magnetic field or force is the strongest, right? And can you draw the magnetic field line? Okay, so make sure you know how to draw it. And yeah, so why magnet becomes a magnet? So it's due to electrons, right? So electron are moving charge, okay, and when there is a changing current, okay, when there is a moving electron, there will be a changing current, right? Di over dt. So for electricity to happen, we need to have changing charge, which means the charge moving. But in order to have magnetism, we need to have changing current, right? Which means that there is a alternating current, di over dt. So the current must not be constant. If the current is constant, so we won't have magnetism. Okay, so we only have electricity, but in order to have the magnetism, we need to have a changing current, di over dt. Okay, so this is for electricity. The condition is the charge can be stationary or moving, so it doesn't matter, right? But for magnetism, we cannot have stationary charge merely. We need to have the charge must be moving so that we can produce changing current. So this is just what we have learned in previous class, that potential difference exists between the battery terminals, positive and negative, where the charges accumulate on this side, positive and negative. So when there is an electric field, I have mentioned this, that when there is an electric field, then there will be a potential difference across the charges, right? So this is the equation you have learned. The first two lines is we have learned in the first line is what we have learned in previous chapter, and the second and third line is just the application of differentiation in maths class, right? So this is, make sure you know how to draw the magnetic field line. So make sure that the field line must be sourcing from the north pole to the south pole, right? And we characterize that as the B field or magnetic field. What if we cut this magnet into half, right? Exactly half. Then can we have a individual pole, like north pole individually and south pole individually? And according to physicists, right, named Maxwell, so he was the one inventing or discovering Maxwell equations, important topics or equations in physics. There is no magnetic monopole. Monopole means the individual poles, but for charge we have dipole, which means we have positive and for charges we have monopole, which means that the positive individually and negative individually. But for magnets, we cannot have magnets which only have one pole. No. So north pole and south pole must coexist, which means that they exist as a pair, right? So magnetic monopole does not exist. So you always have the pair of north and south. So no matter how you cut it into half. So the application of electromagnetism. Maybe you have seen these pictures. So this is the maglev, magnetic levitation train, in Japan actually. And how it works you can find out on YouTube, but just a general idea. So when you have let's say a superconductor, and then you just cool it, then there's a interesting and quite strange phenomena happens, where when you put a magnet on top of it, then the magnet can just floating, and yeah, it's sort of like flying, but yeah, all of it occurs because of this physics, electromagnetism, right? So make sure you need to have very cold liquid like liquid nitrogen for it to works. And the second one is electromagnetic crane. I believe you have seen this. So this crane, it will lift any like steel or magnetic objects that attracts to magnet, and it will be easier for them to throw this rubbish away. So it works on the principle of electromagnetism or electromagnet. So what is electromagnet? So it's just a permanent magnet or the temporary magnetic field being created on the steel, right? So it's just like a steel nail. You just connect to the wire, and then you just coil it around, and you will have electromagnet, right? So that's simple as it is. But let me draw some stuff here. So can we determine the north and south pole? So yeah, we will discover later. So one hand rule we call, so this is right hand rule. So I will I have drawn there. So this is the hand rule. You just put your thumb, okay, according to the finger. So this finger must be the circulating current, the direction of the circulating current, right? And then this is the field, magnetic field B. So the direction of the field will determine the north pole N, right? As easy as it is. So I will show you how to use this hand rule later. Okay, the question is how a magnet become a magnet really. So we just discovered that electron is the major contribution to magnetism, right? So let's see. So magnetic versus non-magnetic metals. So these are the metals which attracted to magnet. The first row you can see is iron, nickel, cobalt, and steel. So steel is just the alloy material combination of iron and carbon. So that's steel. And what about the non-magnetic? So non-magnetic is if you place the aluminum or lead nearby to the magnet, so it won't attract it to the magnet itself. And this is the example. So we have gold, okay, silver, brass, copper, and so on and so forth. Okay, so how magnet becomes a magnet? So you need to know that in magnet, of course, magnet composed of atoms, right? So this is, let's say this is the, without the circuit first. So this is the, okay, this is the initial state, let's say. So in iron we have so-called the domain. So this one, let's name this domain. This one is the domain. All of the part here I call it domain of the iron. So each domain they have tiniest magnet, which is the electron. So you saw here I just label this as a line. This is actually electron. And electron, they have their own orientation on this domain. Let's say the orientation is like this direction, and for this electron is in this direction. So in each domain they have same directions, but per different domain they are different. I mean, per different domain the direction is different, but in the same domain, okay, they have similar direction as indicated here, right? So I hope it's understandable. Let me just delete everything. So the red and also the blue line is actually electrons, right? And when we coil the wire like this, when we coil the wire, of course there will be a current moving. There will be a changing current, okay? There will be current, let's say, around this coil, wire coil, right? So there will be a current circulating, right? Circulating means, let's say you have learned physics, right? Force and motions. In circular motion, the acceleration is not zero, so it tends toward the center because you have the direction change, right? Same goes with this. Initially, right, the current is, let's say, constant, but because the current is circulating, so you have changing current, right? So that's how I usually understand it. We have a changing current, so this will create a magnetic field, right? It will create a magnetic field. Okay, just remember, just now I said that when we have a changing current, you have a magnetic field, right? Fair enough. Same goes with this. So you have a changing current, so there will be a magnetic field. So the magnetic field, I call it B external. So this is the external magnetic field outside created due to the circulating current. So when there is a circulating current, just remember like this. The rule of thumb is when you have a circulating current, you have a changing current. When you have a changing current, then you have a magnetic field, external. So what is the direction? So the direction is this direction. So this is the direction of north, because the arrow pointing here, and this is the south, right? So simply like that. But how can this circulating current cause magnetic field, and how can this magnetic external can cause the magnetism overall? Because the action of the magnetic field, the B external, will interact with the internal magnetic field. So the internal magnetic field is this, the electron in each domain, right? And then this B external will interact, and then it will causing the electron to be directed in one direction. So initially this electron pointing here, pointing like this, and in other domain it pointing like this. So it's very random, but because of this B external magnetic field, so all of them will be directed in one direction, okay, which is in this direction. So what is the conclusion? The conclusion is you apply the B external due to the circulating current just now, and then this B external will interact, will affect the internal magnetic field, the electron. So it will divert the electron to be in one direction in all domains. So when all domains is in one direction, then we have the addition of vectors in one direction, which means that this one pointing to the north. So when we add up, so overall this will be a north pole, and this side will be a south pole, right? So this is the addition of vector. You just add all the vectors in one directions, and the sum of it will be the resultant, let's say resultant force or resultant field. Okay, so this is all the basic you have learned. Okay, next one. When I remove the battery, then unfortunately it will return to the original state, okay, where you see the direction of each domain, direction of the electromagnetic field will be very random, okay. Okay, so how to make a permanent magnet? So one way is just naturally, okay. Naturally means that the domain already oriented in such a way, right? It's only in one direction, it's not random anymore. And then the second one is to rub the magnetic object. Let's say you have a magnet and you rub against the steel or needle, then that needle will become magnet. Because what? Because of the orientations, because you apply the B external, and then the orientation of the domain will directed or will orientated in one directions. That's the reason why, okay. And then the question is, then how Earth can generate its magnetic field? Is it due to the similar concept like this? What do you think? So you may find the answer. So make this as a homework for you. Okay, so we will discuss in the next class perhaps. And then why steel can be magnetic but not gold or silver or plastic? Because the only one that can be magnetic is ferromagnets object or material. So this type of material is the only one that can be magnetic. So there are usually three types material we have learned: magnetism properties, which is diamagnetic, paramagnetic, and ferromagnetic. So the one I have explained, the domain things, is ferromagnetics. So it's very simple. But for diamagnetic and paramagnetic is the object that cannot be magnetic, right? Why? because the diamagnetism is actually when you apply the external field. This is external, so the direction of this electron magnetic field will be in the opposite way, right? So that's diamagnetic. Okay, and silver is the diamagnetic, which means that when you apply the let's say magnet around, okay, so it will repel the magnet, so it won't attract the magnet. And for paramagnetic material, so the orientation is very random. So when it's very random, so there will be a wick when you apply the external field, so there will be a wick magnetic field produced. But for ferromagnet, so in each domain it's not random, right? In, let's say this is one domain is actually in one direction, one domain, but when you apply the magnetic field, this domain will direct it in one direction, as I have explained just now, right? Okay, magnetism effect in current carrying conductor. Current carrying conductor is just a wire, right? It's just a wire. Okay, so let's say we have a current inside flowing inside let's say a silver or conductor, and this current is changing current, let's say the IDT. So when there is a changing current, there will be a magnetic field, right? So that's the principle we have learned. So we can use the right hand grip rule to determine the direction. How? Just now I already demonstrated, but I will show you how to apply it. So you just put your hand, right hand, and then you just make sure the thumb, okay, this thumb is directed to the current, so in the same directions, and your finger, this finger must be the resulting magnetic field, which is in this direction. Okay, so you imagine that you have a field, circulating field, okay, which is counterclockwise. But when you see this field in this region, in this part, so you can see that there will be a field which is into the page. This is into the page, and there will be a field here which is out of the page, right? So you have two regions, top and bottom. So the top one is out of the page field, and the bottom one is the into the page, right? But what is out of and into the page thing? Okay, you might wonder. So imagine you have arrow. So let's say this is the first one. This is the back of the arrow, so it will mark as X, and this is the top. The point. I mean the tip of the arrow, which is dot, right? So when something into the page, when there's a vector into the page, into this paper, so we see the X, we see the back of the arrow. But when it is coming out of the page, we see the tip, okay, the tip of the arrow, which is the dot, right? It's very easy. So you just imagine this vector, the magnetic field, okay, going into the page. You can imagine it's going into the page first, and then it will goes out of the page at the top. So that's why this is out of the page and this is into the page, right? So you can imagine it in that way, maybe. Okay, so same goes when you have the current in opposing direction, okay, going to the left. So we will see the opposite thing. So the magnetic field will be clockwise, right? And later we will discover that when there is changing magnetic field, okay, just now it's changing current, but later we will learn that changing field will cause current to be induced, right? So what if the current circulating inside instead of the field, magnetic field? So same thing, we can use right hand grip like this. So but now the finger will be the current, So this finger, this 1 2 3 4 finger will be following the current directions, and this thumb will be the fill, and the fill must be at the north side. I mean, the thumb must be directed to the north side. Okay, the thumb must be directed to the north side of the electromagnet or magnet, right? But previously you see that the finger, okay, the 4 fingers will be the fill, the circulating fill. But now, because you have circulating current, so the current will be the direction of the finger. So you just put your finger according to the direction of this current. So the current is going downwards, which means that your finger should be going downwards, which means that your thumb will be directed to the right. So which means that your north pole is there, right? It's very easy to determine. Okay, next one. Is compass north really showing Earth north pole? Is it? Or is it like this? So when you have a compass, is the compass really showing the north pole of our Earth? Because when you heard someone saying the north pole of the compass, so is they really mean the north pole of the Earth, or is it there's something else? So is this logical, you think? Because if you realize that when you have a magnet, if you say that this compass is showing the north pole of the Earth, so it is the same thing. You are saying that you have 2 magnets, because our Earth is a magnet, right? Earth is a magnet and compass is a magnet. So when you say that this compass showing the north pole of the Earth, so it is the same, analogously, same thing. You are saying that this magnet 1 is showing or directed to the north pole of the magnet 2. So they're kind of like attracted to each other. Is that logical, you think? No, right? So the north pole is supposed to be attracted to south. So which means that this pole, north pole of the compass, this is the compass, right? Compass. This compass will shows the direction of the south pole, north pole, because this north pole of the compass attracted to this, and this south pole will be attracted to north pole. Okay, so that's the thing. Okay, let's see if I have another slide here. Okay, I think it's finished. Yeah. Okay, so that's all for 1.5 hours, but I've already make it compact into maybe not even 1 hour, but yeah, that's the thing. Okay, yeah, in the next class we are going to dive through more on the current carrying conductor, and also the, let's say, the magnetic force, right? Magnetic force, how to determine the magnetic force if you are given, let's say, the field and also the current, right? So I will yeah, we are going to learn together on that, right? So that's all, I guess. Thank you very much for let's say watching. Okay, and yeah, have a good day. Bye bye.